Good morning, students. This is the last class. I think this is the last class to complete this moving charges. I think one more thing I have to say. Today is your result day. I think you are going to get your result shortly. But don't get any tension because I know all members. I think all members. I think you are promoted to the second year. Nobody is scared. And the free members are worrying about your percentages, but don't get any tension and worriness regarding your percentage because you may short of 80%. But first year, I already told you several times in the class, because first year you didn't get the much time to concentrate on the subject. So that is the reason second year you have enough time to score, to cross the percentage more than 80%. So that is the reason once again I'm requesting you, if you get more than 80% and don't be in a high, and if you get less than 80% also don't get depressed, because first year cannot decide your future, so only second year decides your future. So once again I'm saying all the best, all the best, and be concentrated on the classes only, because what are the bygones things are happened, there is over, there is bygones are the bygones. So the present situation is so important, so that is the reason I'm requesting you all the students to concentrate on this second year only. Now in this class we'll focus on two topics, namely moving coil galvanometer, how can you convert the galvanometer into ammeter, and conversion of galvanometer into voltmeter. See, the conversion of galvanometer into ammeter and conversion of galvanometer into voltmeter, both are highly important questions for PUC point of view and objective point of view, and also these concepts are very easy. So once if you consider it, then you can write in the examination very easily. So let's go to the topic, namely moving coil galvanometer. See, a moving coil galvanometer is nothing but MCG. I think in first year so many students are very much interested in cricket. I am also cricketer. So MCG means immediately we are thinking it is a Melbourne cricket ground. But don't think it is a Melbourne cricket ground. That is also abbreviation for this Melbourne cricket ground, but it is MCG, stands for moving coil galvanometer. Now see here, in this moving coil galvanometer, what you have to do? What is this moving coil galvanometer? See, moving coil galvanometer is an instrument used for measuring the currents. Especially this moving coil galvanometer is useful to measure very small currents. Very small currents in the sense 10 to the power of -8 amperes to 10 to the power of -10 amperes. Such a small range currents we can measure by using moving coil galvanometer. Now for this construction and working and the diagram and everything, now we'll see on the board. See, in this first moving coil galvanometer, first we have to take one powerful horseshoe powerful magnet. One is north and there is south. See, this magnet is curved. Curved means it is always producing a radial magnetic field. Now inside this magnets I am keeping one rectangular coil. I am keeping one rectangular coil. The lower portion of rectangular coil I am attaching one spring, and that is connected to one terminal, the terminal named T1. The upper portion of the spring is connected to one mirror, again top is connected to one torsion head. And finally, these two terminals are connected to T1 and T2, that is nothing but battery. T1 and T2 of the terminals of the internals of the battery. Now inside this coil, I am keeping one iron rod. If I am keeping that iron rod, the strength of the magnetic field can be increased. So for that reason, I am keeping here one iron rod to increase the strength of the magnetic field. Now this mirror is used for, suppose if the coil is placed in a magnetic field, it will be deflected. Then the deflections we can measure by using this mirror, that is a lamp and scale arrangement. For that purpose we are using this mirror. Now yesterday in the last class we already know, if any rectangular coil, if it is placed inside a magnetic field, then it will experience the torque. How much is the torque? The torque experienced by the coil is given by torque tau is equal to BIAN. Torque tau is equal to BAN sin theta, and sin theta, if theta is equal to 90 degrees, then the theta can be neglected. And finally here we got, because here the two terminals are connected to a battery, then electricity is passed and the coil current is passing through the coil, but this coil is placed in a magnetic field. Because of that one, the coil will experience a torque. The torque is given by tau is equal to BIAN. Now once the coil, see once again, suppose this is the rectangular coil. If the rectangular coil is placed between the magnets, because of that one, it will experience the torque. It will experience the torque means it will be moving like this. Once it is moving like this, this coil is attached with one wire. This wire is made up of phosphor bronze wire, because it has Young's modulus and low rigidity modulus. So that is the reason phosphor bronze wire is preferable. Now if that wire is attached, the phosphor bronze wire is attached, then what is happening? If the coil is moved, then that wire will be twisted. Because here the wire is attached. If the coil is moving like this, then the wire is twisted. Then if the wire is twisted, within the wire a restoring torque is developed. Then that restoring torque, I can give equation. This is applied torque and this is restoring torque. This is applied torque, this is restoring torque. This restoring torque is nothing but, it is given by the equation C theta. What is that C stands for? The C stands for couple per unit twist and theta stands for deflection of the coil. And this is the applied torque. This applied torque is due to when the current is passing through the rectangular coil, which is placed in a magnetic field, which experiences the torque. The torque is given by tau is equal to BAN, and this is the restoring torque. Restoring torque is nothing but TR is equal to C theta. Under equilibrium, the applied torque and restoring torque both are balanced. So at that condition, TA is equal to tau A is equal to applied torque is equal to restoring torque. Then I can write BIAN is equal to C theta. And finally, I is equal to C by BAN into theta. In place of C by BN, if I am taking one constant, it will be I is equal to K theta, and finally it will be I proportional to theta. This is the principle of moving coil galvanometer. What is the principle of moving coil galvanometer? When the current is passing through the rectangular coil and deflection is produced, and this current and deflection both are directly proportional. So once again, all of you see the explanation part and everything. See, in moving coil galvanometer, what is the principle? When the current carrying coil is placed in a radial magnetic field, torque is produced and the wire is twisted. Within the wire, restoring torque is developed. Under the equilibrium, the applied torque and the restoring torque both are balanced. Now here, you see here, this is the magnetic field produced, and this is curved. It is concave shaped. Because of this concave shape, it produces radial magnetic field. So every time the coil plane and this one is perpendicular, and this rectangular coil is insulated wire, it is placed inside this magnetic field, and this wire is made up of crossbar branch wire because it has Young's modulus and Rho resistivity modulus. And this wire, the top portion, it is attached with one mirror, because every time if the coil is deflected and this mirror also rotated, then from this mirror we can measure by using lamp and scale measurement, we can measure the deflection. And the top portion of the wire and the bottom of the wire, it is connected to terminals, because this terminals we call it as a T1 and T2. Those are the battery terminals. Once the power is given, electricity is passed, current is passed. Once the current is passed, the coil is experiencing the torque. The torque is, when the coil is placed in a magnetic field, it experiences the torque. The torque is given by BAN sin theta. Your theta is equal to 90. That is the reason I am taking TA is equal to BAN. Because the coil is rotated, the wire is also twisted. If the wire is twisted, restoring torque is developed within the wire. The restoring torque is given by TR is equal to C theta. TR is equal to C theta. Under the equilibrium, applied torque is equal to restoring torque. So that is equal to BAN is equal to C theta. So I is equal to C by BAN into theta. Here I am taking this is constant. So that is the reason I can get I is equal to K theta, or finally I proportional to theta. And finally from this expression we can get the deflection produced in the coil is directly proportional to the current passing through the coil. The deflection produced in the coil is directly proportional to the current which is passing through the coil. Now from this expression we may get two more definitions, that is, see, BIAN is equal to C theta. BIAN is equal to C theta. Now if I am taking here theta by I is equal to BAN by C. This we call it as a, this equation we call it as a current sensitivity. Current sensitivity. The current sensitivity is nothing but the deflection produced in the moving coil galvanometer per unit current. The deflection produced in the moving coil galvanometer per unit current, that we call it as a current sensitivity. If the deflection is divided with current, then we can get a current sensitivity. And similarly, if the deflection is divided with voltage, then we can get a voltage sensitivity. Similarly, see, theta by V. Theta by V, I can write it as a theta by V is equal to IR. Now theta by I is nothing but we can get BAN by CR. BN, because already theta by I value, this is same value, so finally you can get theta by V is equal to BAN by CR, and this we call it as a voltage sensitivity. This is called voltage sensitivity. What is the meaning of voltage sensitivity? The deflection produced in the moving coil galvanometer per unit voltage applied to it. Or simply, deflection is divided with voltage, then we can get voltage sensitivity. This is current sensitivity and this is voltage sensitivity. Current sensitivity is nothing but deflection is divided with current, and voltage sensitivity is nothing but deflection is divided with voltage. That we call it as a voltage sensitivity.